So first fundamental theorem of calculus. That's what we did yesterday. And that's what we just did with numbers 4 and 12. If you antiderivative a derivative, you get back to the function. Just be careful with the a's and the b's, smallest to biggest, and then top minus bottom. If you rearrange things, so this isn't a separate equation. I'm not even going to box it because it's not like, oh, let's go memorize this one too. Like, no, all we did was move f of a to the other side. And when we write it like this, it can take on a little bit different, or it helps us see a little bit different meaning. Sometimes the first fundamental theorem is called the total change theorem. If you're given the rate of change of a function, so if you're given f prime, you can find the accumulated change. In fact, that's what that integral represents, the accumulated change. Because you're adding up all the area of the change, right? F prime is how much is the rate of change. But if you add up all the rates of change, you get the total amount of change. What's a better one to look at? Which example should we see? Skip down to number 4. No, back up. Number 3. If the rate of growth of a population is dn dt, or n prime if you like, then this is true. Like that's, and I mean this statement is true regardless of what n represents. But that represents the increase in population. So that's the accumulated rate of change, or the accumulated change. Accumulated change, or just the total change. Maybe this is an even easier way to say it. If you integrate a rate, so if you antiderivative a rate, you get the total change. In fact, we can even put the labels on here. If you integrate the rate from A to B, you get the total change from A to B. So this is still the first fundamental theorem of calculus. It's just a little bit different application of it, a word problem application, rather than just saying here's f prime, find f. It's like we can do this with word problems. Number 4. If w prime is the rate of growth of a child in pounds per year, what does antiderivative from 5 to 10 of w prime represent? Well, one way to do it would be just to write out what it means. I mean, that would be w of 10 minus w of 5. So what does that mean, like in terms of the problem? What would we be finding if we evaluated this? Do you know? What was that? Total growth in pounds. You can also do kind of a unit analysis on this to come up with some of these answers, because w prime is pounds per year. dt, so remember that's like the width of that rectangle, that's years, or change in time, which is years. So pounds per year times years equals pounds. So sometimes looking at the units can help you figure out what you're finding. Number 5, if oil leaks from a tank at a rate of R of T gallons per minute, what does that thing represent? So I like these questions because there's no math, like there's nothing to find or compute. You don't need a calculator. It's just concept. What does that integral mean or tell you? Anybody? Yeah. Gallon. Oh, careful. It would be the total gallons leaked or lost from 0 to 120. So not per minute. R of t was in gallons per minute. dt was in minutes. So that answer is going to be gallons. Whatever it is going to be gallons. But it's the gallons that we lost between 0 and 120. Do 6 and 7 and then we'll move on. A honeybee population starts with 100 bees and increases at a rate of n prime bees per week. What does this thing represent? I'm not going to call on anybody, but see if you can look at that and think through what that whole thing represents. So 100 was the starting population. The integral of a rate gives us the total change, or if you want to do it in units, n prime is bees per week, dt would be weeks, and so this is in bees. It's the total change in the number of bees between 0 and 15, or the change in population from 0 to 15. So start with 100, we add our total change. Our answer then would be the number of bees after 15 weeks. So some good questions there to make us think without actually making us do the math. You know what? Let's do one more, because these are popular AP type questions. A cup of coffee is at 90 degrees, is put into a 20 degree room when T is 0. The coffee's temperature is changing at a rate of that thing. Find the coffee's temperature when T equals 10. Okay, well, we know that if we integrate a rate, we get the total change. So if we integrate, oh, this one's kind of like the pizza problem we did yesterday, but this time they put the negative on there for us, so we're good with that. We'll go from time equals 0 to time equals 10. Now, there's kind of two ways to set this up. You could say T0 plus this would get you T10. Or, if you want to do how we set it up yesterday, you could just start it off by doing it that way. T10 minus T0. And then move the T0 over. So, this worksheet is trying to get you to set it up the other way, but I think this is more consistent with what we did yesterday, and the only price you have to pay is you move the T0 over. That's a calculator problem right there. And then we add T0 is 90. And you can just trust me, and then we'll move on. 67.828 degrees Celsius. All right, so the assignment from this worksheet is 8 through 11. And with calculator, so I don't expect you to integrate the square root of 1 plus e to the t by hand. That would be tricky, impossible, probably. All right, so that's sort of finishing up first fundamental theorem. And the first fundamental theorem is if you antiderivative a derivative, you get back to where you started from. All right, let's talk for a minute about the second fundamental theorem.